about. Then one item which is very critical is to have some discussion about the importance or the fundamental understanding of the mechanics and the material removal and the mechanisms for material removal of CFRP, composite material. Then from that, we were able to develop, I would imagine it's very unique, mechanistic force model in order to be able to predict forces in the cutting of CFRP using superabrasive tools. Then, of course, once you have a model, you need to validate that experimentally. And then I'm going to show some applications of this model and some concluding remarks. As you know, the aerospace industry is quite important sector. For example, if you look at last year or two, that the contribution of that sector to the aerospace and defense industry worldwide was in the neighborhood of $760 or $800 billion a year. So it's quite significant one. When you look at the use of composite materials in aerospace, it's growing very steadily. At the moment, if you look at some of the aerospace structures by Boeing or Airbus, for example, you find that the percentage of using composite material is almost around 50% or more. The drilling operation is very critical. Some of the structures you can see or you can have to make holes up to 50,000 holes in one aircraft, for example. There are some issues here. There is the economics of the process. Also, there is the quality attributes of the product. And more important, you have to make sure that you are getting damage-free structure. And when I talk about the damage, there are many types of damage. The most critical ones are the delamination of the plies of the composite or thermal damage. These two are the most critical ones. And they can be controlled. If you control the forces to be below certain critical level, then you can eliminate delamination. It depends. If you are talking about entry delamination or exit, then you control the cutting or the axial force, tangential or axial force. Thermal damage, of course, you have to make sure that the temperature doesn't exceed the decomposition temperature of the polymer being used. How critical is that? I'm sure you understand how the aerospace is spending lots of effort on solving this problem. And it is also known that some of the fatigue fracture happens in the fastened holes. Could be 90%, up to 90% due to the damage in the plane. Okay, so it is critical that we have to make sure that we are controlling the process. If you look at how to control the process, you can see that I have to reduce forces and reduce the temperature. The conventional way of drilling, as you know, that you have a tool which is advancing axially, you have continuous cutting process. But the best way to reduce the forces and temperature is to make it intermittent. So that means you are using some kind of vibration-assisted drilling or some kind of orbital motion in such a way that you are not touching the tool, the tool and workpiece are not cutting continuously. So by imposing these two types of movement, you can eliminate the dwell at the center. Like in conventional drilling, the center of the drill is at zero velocity, and that increases the forces. So by imposing some kind of velocity vector or velocity at the center through the vibration-assisted drilling or the orbital drilling, you are reducing the forces this way. But also you have some kind of cyclic engagement, which can cause some kind of cooling effect. And if you can see on the slide that due to the rotation of the tool in the gap, which is created by orbital drilling, of course, you create some kind of hydrodynamic instability. You are creating some kind of vortices, which will encourage or promote significantly the cooling effect. When I'm talking about in this discussion, I'm only focusing on the orbital drilling. I'm not talking about the VAD. And simply speaking, that you have a tool that can be used to make different holes. So this is the advantage of the technique, that with one standardized tool size, you can create and control different hole dimensions. Of course, this process also helps a lot in terms of helping the evacuation of the chips out of the process, out of the workpiece. The objectives of this work is, as I mentioned before, the first one is to have fundamental understanding of how the superabrasive tools can cut into composite material. And my focus here is on the carbon fibers in particular, but the model, of course, applies to any other fibers. So fundamental understanding means that I have to understand what is the effect of the orientation of the fiber relative to the direction of motion, the effect of the grain orientation, and because that will affect a lot the mechanism of cutting, as we will see shortly. And once I know that, I can identify the failure modes. So when I'm doing the modeling for the forces, I understand which mode of failure is causing the cutting. So my modeling or my predictions will be more accurate this way. In order to achieve that fundamental understanding, we did some kind of scratch test while using single grain, but also we have to have finite element modeling in order to understand the mechanism itself or the mechanics of the cutting. The second objective is to extend this knowledge about single grain into multiple grain. And that creates the model I'm looking for that can be used for, I can test that or validate that work on some kind of flat grinding test. Once I'm sure I have confidence in the model to deal with this one, I can move into the orbital drilling. And in this case, I can, of course, I need to do some tests, basically to understand some of the features and the characteristics of the orbital drilling to make sure I'm including that into my model. But also this test will be very critical in order to achieve the fourth objective, in order to validate the final goal of having orbital drilling model. Once I have the model, I can use it in many aspects. I can optimize the process itself, because now I know how to predict forces. Once I know the forces, I know the energy, then I can eliminate delamination and thermal damage. And beside optimization of the process, I can also optimize the tool geometry. And that's a critical issue because most of the industry are relying on the knowledge coming from metal cutting to design tools, which is not the same at all. One is based on plastic deformation, the other one is based on fracture. So the theory or that model will help us to optimize tool geometry, and I'm going to show a little bit some of these results. At the end, we could also develop new processes, and that's what we have done recently, that we proposed another kind of tool, hybrid tool, which has superabrasive and single cutting edge together, and also the oscillatory orbital drilling, which we presented at CFRP a couple of years ago. Okay, so on the first side, for the fundamental understanding, we are using some kind of single diamond tool, which is used for dressing and grinding, in order to look at what will happen if I'm cutting the fiber or the composite material under different conditions, which are stated in that table. We also needed, as I mentioned, we need to have finite element modeling. So we are assuming some assumptions like it's plane stress. The element size should be very small to deal with the dimensions of the fibers. So the element size in the 2-3 macrons. We had to separately model the fibers and the matrix, the polymer, and also the substrate, which is the other section of the process. Now, for sure, we have to consider the cohesive interaction between the fiber and the polymer, because that's one of the modes of failures. And some other assumptions are, of course, has to be made, like the coefficient of friction and so on. The important part after that is we have to find a way of predicting when the damage will initiate and evolve. Because once I know that, I can model my process of cutting, knowing how it will be failing. Okay, so I'm using the Hashing's damage model, and we are looking at different modes, mainly the tension and the compression failure of the fiber, and the same for the matrix. Again, for the cohesive contact between the fiber and the matrix, we are using the traction separation law. Okay, so what we did, we looked at what will happen if I am cutting and the direction of motion is parallel, or I have zero angle between the direction of motion and the fiber orientation. So I'm using that simple test. And of course, we are expecting to look at, from the analysis, we realize for sure, as expected, that we have some kind of stresses in the longitudinal and transverse direction. So this will be L for longitudinal, and this is compressive stress. And also we have compressive in the transverse, perpendicular to the fiber axis. Of course, because of the low interfacial strength between the fiber and the matrix or the polymer, we would expect that will be some kind of debonding will easily happen. And as a result, the loading coming from these stresses will cause some kind of bending. And this, I'm showing also some of the results we saw already after doing the single test. And we can see right away that we have the bending failure mode, but also we can have the lateral fracture in the compression transverse direction. So from that, we know that when you are at zero orientation or relative angle between the fiber and the direction of motion, this is the kind of mode of failure we're expecting. We repeated that, the same kind of test for different angles, like for 45 degree. And again, we saw that the compressive or the longitudinal compressive stresses coming from during the cutting will, through the Poisson effect, creates stresses in the tangential or in the tension direction, and this will be transverse, perpendicular to the fiber. And this kind of stresses are causing the transverse tensile fracture, as you can see here, that the fracture is across the fiber itself. We want two other angles, like 90 degrees. So we want 0, 45, 90, and 135, or minus 45, which is 135. So again, what we noticed here that the stresses are similar to what we have in the 45 degree. However, that we didn't see the fracture, the transverse fracture. And that's really coming from the fact that because of the orientation, the included angle between the fiber direction and the rake face of the grain is much larger than if it's around 45 degree. And as such, the contact pressure for 90 degree will be very high, and that caused the change of the mode. Of course, there is not enough time to talk about all the details, but I'm just showing the general information. Well, I'm showing here, for example, how we are using the damage criteria from Hashin's model to predict the evolution of the damage. So here, for example, you can see, if I look at the damage variable, which is, we are calling it D, between 0 and 1. 0 means no damage, 1 means it's full damage. You can see from that, when the orientation is around 45 degree, then we are expecting to reach that level of damage variable 1 at the value of 1 when we are dealing with transverse fiber tension or longitudinal fiber tension. And that's what we expected from the results and from the sketch test. The same thing we can see for the 90 degree, and here we can see the evolution, and we end up with different modes. We have here longitudinal fiber tension and longitudinal fiber compression. So we established the knowledge fundamentally about the effect of the orientation of the fiber relative to the cutting motion. Once I know this information, I can put that in my model, and then I can make my estimation of the cutting forces. So the first step for sure to deal with the force prediction is to have some information about the modes of failure, which we already established and I discussed. The second one is we have to know the contact area between the grain and the fiber, and that depends on the cutting kinematics. So I have to make sure that we are familiar with that. So the methodology, after knowing the failure modes, we go into the kinematics of the single grain cutting. Then from that, we can find the forces per grain, multiply them, and get the total force if I know the number of grains. Of course, it has to be idealized based on an average value, knowing the grit size of the tool. And once I know the total energy, the forces, then we can get the final model. So if I start with the kinematics of the single grain, it's very close to actually to the cutting or the grinding process. So the arc of the cutting, we can divide it in 2 zones, and each zone will be divided later on in the final model into 3 regions. And we can, in this case, we can include the effect of the orientation 0, 45, and so on, approximate that within for each region. And once I am familiar with the shape of the undeformed chip, of course, the thickness is varying from 0 at the entrance till a maximum value, let us call it HM. And this is very fundamental parameter, which we can see coming in all the formulation. And that parameter, which is we're talking about, which is the maximum undeformed chip thickness, is function of number of parameters. One of them is the number of grains per unit area. Let's call it C. The radius R, the chip width to height ratio, which we can find from the scratch test. And we can, in our test, the average value was around 3.2, so we can use this value. Then I need to know, of course, the HM, or the thickness, of course, depends on the workpiece feed rate, the cutting speed, as well as the depth of cut and the equivalent wheel diameter. So knowing this information, I can estimate the value of the undeformed chip thickness. As I mentioned before, it varies from 0 up to the maximum value linearly. We have assumed to be linearly changing. And that's important also to consider that effect, because as we'll see later, it affected the force predictions. Now, the question is, we need to predict the forces now for a single grain, as we mentioned before. If you look at the process, we have 3 components that add up into the total force. One coming from the blowing force, friction force, and also chip formation force. Once I calculate each one, I should be able to sum them for a single grain and then integrate that into the total force. So I think everybody in familiar with machining or metal cutting, for example, you know that when the depth of cut is very small, you don't cut. In fact, you are displacing the material. You're causing it to, it's like blowing effect. And that will result in pushing the grains on both sides of pushing the fibers on both sides of the grain in normal direction to that fiber, and that the energy required to cause fracture of the fiber is that what I'm looking for to realize what is the conditions that result in failure of the fracture and the fracture of the fiber. So that is coming, of course, from the blowing force itself. So the deformation energy, if I equate it with the fracture energy, I can estimate the strain that is reaching certain level and causing the fracture. So for a single grain, this force is function of some parameter, let us call it KHI, which is the blowing, as I mentioned before, the blowing force is critical when the depth of cut is very small. So that's why at the entrance, it has a value of 1. When I'm exiting the cut, when the thickness HM becomes the maximum value, that parameter becomes 0 because the component of blowing is diminishing. So of course, this force is function of some kind of stress causing the failure and some kind of contact area. So one can make the estimations of these parameters. And at the very end, this will be function of the strength of the fiber in the tangential, in the transverse direction under compression. It's function also of the modulus of elasticity in the transverse direction, and also the void fraction, the volumetric fraction of the fiber within the material. And in terms of the area, it's function of the ratio I mentioned before, R, which is the chip to height ratio of the scratch, and the maximum value of the unformed chip. By doing the proper summation, I can find now the total force coming from the blowing action. And this is again a function of the same parameters I mentioned above. But here I have to consider the width of the cutting area in contact between the tool and the material, and also the length of the contact arc. So once I know this information, knowing the grid size, I can estimate the total number of contact points or grains in contact with the material, and from that I can find the total ground force. I should repeat the same thing now for the friction force. Again, if you look at like this triangular here, represent a one grain, and if it's interacting with the fiber, the composite material, then I have the stresses in the normal direction of the fiber orientation and parallel or along the axis of the fiber. And this is my fiber. Again, through very lengthy analysis and so on, we know that, as I mentioned before, we are having some kind of debonding is happening along the fiber, but also we have bonded fibers underneath the rake, which is in the substrate or the area below the cutting region. And I have to add these two components to calculate the total friction force. Okay? So I have to consider the parameters coming from the metric yield stress. That's when I'm compressing the material below the rake. I have to consider the interfacial strength, that's what is causing the bonding. And of course, very critical for us is the angle between the fiber and the feed or the motion direction. So that will end up with some kind of a formula. I'm showing all my formula in functional form because it will just to show the effect. We're not talking about the exact equation here. So the frictional force will be function of these parameters I mentioned for the interfacial strength, the yield stress of the matrix, the volumetric fraction of the fiber, the parameters I mentioned before, C, this is the equivalent diameter, and so on. And more critical for us is the effect of the relative orientation or orientation of the fiber relative to the motion. This is very critical in our calculations. Then comes after that is the chip formation force, the third component. And this one comes from, we are dealing with three different modes. Mode 1 for bending, mode 2 for longitudinal compressive failure, and mode 3 for transverse compressive failure. Again, this is, as I said, the initial discussion we had with Finite Element and Scratch give us this information to build on it. Once we have the bending, of course, and we have also the bonding happening, then for sure that will cause the bending, which means the longitudinal compressive and tensile forces or stresses are acting at the same time because of the bending action. Then from that, I can find the information about the total force coming from the chip formation, which is mainly function of the fiber volume fraction, function of the stress generated, which is tensile and compressive. Sorry, it's compressive, but coming from the longitudinal and the transverse directions, and of course the chip formation area, which is function of the orientation. So that's this parameter again. So once we have these three components, we add them up, but we have to validate our work. So we did first some kind of flat surface grinding. So it is very simple experimental setup. And from that, we looked at our predictions from the model versus the experimental results. And you can see here, it's quite in very good agreement, considering that we are dealing with two different types of grains for 120 grades and 60. One is the electroplated, the other one is brazed grains. So this gives us good confidence that model is working very well. We did also lots of validation for the different orientations, 0, 45, 90, for different conditions and so on. And what we found from, well, I'm showing only one example, but what we found that with 95% confidence that our prediction are within plus or minus 5%, which is much more than what we need for this kind of modeling, for this complex process, in order to allow us to design the process and optimize it, and the design tool. Again, we did some comparison for the distribution of the force on the arc. Again, you can see from the graph, the correspondence or the agreement is really in very good shape. And again, the error in these predictions for many tests were within 4-5%. The next step was we need to do now orbital drilling to validate our model. And when we start doing the first kind of test, we realized that because of the small grains of the abrasive material, then the clocking of the tool can take place, which means that the debris coming out of the process can fill the intergrain space, and that requires additional force, which we didn't account for at the beginning, in order to be able to squeeze the debris generated, because now there is no room for this debris to go through the intergrain space. And we estimated that by treating the debris as isotropic material, and we found the additional force coming, it's like elastic analysis coming from knowing the stress times the area, and the stress is coming from knowing the models of elasticity, the bulk, which is function of the transverse models of elasticity of the fiber, and some other parameters. Then we looked at again, validation now with the model after modifying it for the clocking effect. And here I'm showing some of the validation results. This is the setup for the orbital drilling. It was done on 5-axis machine. This is the workpiece material, and the drilling was happening here. The fiber we dealt with is 0, plus or minus 40, 5, 90. It has 6 layers, symmetrical. And it's a very complex structure, architecture. And as you can see, the results that for the prediction of the tangential or thrust force, for example, the predictions are quite very good. In fact, you can see that. Again, I'm just showing for one case. And now we also looked at the fresh tool versus the clogged tool based on the model I just mentioned. And again, the agreement was quite good. So with 95% confidence limit or interval, we found that our predictions for the tangential is 1 to 14%. For the thrust force is around 3 to minus 8%. Again, it's very acceptable, considering the effect of the change of the continuous change of the orientation of the fiber relative to the grain as it moves undercutting. How we apply that model? So we looked at, you can see, I just need to say that the superabrasive is very good because it makes the life of the tool very high, but it has a serious problem that the surface roughness is very poor. That's the main challenge. So we had to find ways of going around that. So one approach is to design a hybrid tool. So the first portion will be the abrasive section, and we looked at different designs, like the ball-ended flat part end of the tool, whether it's ball-shaped or flat, and so on. And then once we do the process of cutting with superabrasive, we can repeat another run with some kind of PCD insert, polycrystalline diamond single tool, in order to improve the surface finish. And when we did that, as I said, we have the two sections, and we looked at the optimal design So the model was used to optimize the design of that section in terms of the grid size, in terms of the shape of the end, whether flat or ball-ended and so on. And we made sure that the forces are below certain theoretical value. So we created, or we were able, with using this model, to make sure that there is no delamination, no thermal damage. And also we achieved the accuracy of the hole as per the standards of the aerospace industry. All right, so here I'm just showing, if I deal with the superabrasive portion only, the surface roughness is very poor. You can see it's around 9 or 10 microns. I'm talking about RA, central average. However, once I have the second cut with the PCD insert, the roughness dropped from 10 to 2. And that's the objective of this design. It worked very well. Then we thought about another approach. In this approach, we are using only the superabrasive tool. We don't need PCD, which is expensive. And we do the process on 2 stages. The first stage is to use conventional orbital drilling. Then, once we drill the hole, we do some kind of oscillatory motion while we are doing, again, another orbital motion. This work was published in CFRP a couple of years ago, so it's detailed there. But again, as I mentioned here, in the first step, which is the conventional, we use certain spindle speed, like say 40,000 RPM, certain orbital rotational speed, and axial feet. In the second stage, where we are oscillating the tool, the same tool, we are using the same kind of rotational speed, but the orbital rotational speed is much lower, order of magnitude smaller, and the axial feed rate is an order of magnitude higher. And by doing that, conceptually, one can see that the intersection between the part or the workpiece and the tool, through the oscillation, I'm dealing with different profiles of the tool, and gradually you can see that's what's happening in terms of reducing the roughness from the original shape to the final shape. Again, this is a good example to show how the roughness was dropping from that value of around, in fact, in this particular case, under these conditions, the roughness went up, can go up to 17 microns, RA. We dropped that into between 1 and 3. So that was very successful process indeed. Well, to put everything in the right perspective and to compare, if I'm dealing or comparing the conventional drilling using tungsten carbide tool, which is the norm of the industry, versus conventional drilling using PCD tools, versus what we are proposing in terms of orbital drilling with superabrasive diamonds or oscillatory over orbital drilling with the said tool. If you look at the relative cost, of course, the tungsten carbide is the cheapest. So if this is my reference point, then you will see that although the PCD is more expensive, but number of holes produced are very high. I'll give you an example for some of the tests. I can get only 7 holes out of this tool, while I can get something like 300 out of this tool, and maybe 200 out of the set, the superabrasive tool. So if I look at the cost per hole, you can see that what we are proposing is actually much more effective, cost effective than using PCD. So if this is dropped from 1 to 10%, now the cost per hole here is only 60% of the reference case. In terms of production time, if I consider the conventional drilling is relatively 1, we have to, we'll see that the same kind of production time or time required to drill 1 hole is the same, but it's doubled with orbital drilling because, of course, the motion is more complicated and that takes time. However, if you take into consideration that the tool life is changed a lot, for example, if I'm using the PCD, instead of drilling 7 holes, I'm drilling 300, so the factor of 45, then you see that, in fact, the production time for the tungsten carbide, I have to multiply it by a factor of maybe 5 to 10, because there are lots of changes of the tool during the machining. After 7, 8 holes, I have to remove the tool, put another one, and that will slow down the process. Again, in terms of the roughness, we achieved with the new design of the tool or with the oscillatory orbital drilling the reference level of around 2, which is needed. In terms of the flexibility, of course, with the orbital drilling, we have much higher flexibility because I'm using a single tool to make different holes. Okay, so practically I can have some kind of control system, which we developed recently for this process, and we can do some kind of real-time monitoring of the process, and then we can adjust the conditions in order to be able to achieve the desired hole size with orbital drilling, for example. So based on that, you can see while the PCD is quite good in terms of the production time, but in terms of cost, for sure the proposed method for the oscillatory orbital drilling with superabrasive tool is much more efficient in terms of the cost, in terms of the quality of the hole. It's matching the PCD, but in terms of flexibility, it's much higher. So to conclude, just to be on time, that as I presented some understanding or fundamental understanding of the mechanism and the mechanics of the cutting and the material removal using the simple single grain experiment and finite element modeling to predict the damage evolution. We also developed the generic cutting force model, what we presented, which with high confidence level, we are able to achieve accuracy within the 8 to 14%. For high-speed drilling, we can reduce the forces and the temperature in orbital drilling, so that's productivity side. Again, we use that model for optimization of the tool and developing new tool, and also to develop new process where we have the oscillatory movement. And again, we're able to reduce